Vi behøver energi til alt, hvad vi laver. Fra produktion af fødevarer til udvinding af alle de råstoffer, vi behøver til at bygge huse, fremstille medicin og til at producere elbiler. Hvordan matcher vi den stigende efterspørgsel på energi, der er over hele verden? Selv efter årtiers søgen kommer 85% af al energi i verden stadig fra de såkaldte fossile brændstoffer, som kul, gas og olie. Findes der reelt noget alternativ på nuværende tidspunkt, som kan tage over eller blive et supplement? Det taler jeg med Mark Mills om i dag. Han er fysiker og seniormedlem af den amerikanske tænketank Manhattan Institute. Tilbage i 80'erne tjente han Det Hvide Husets afdeling for videnskab. Efterfølgende har han fungeret som rådgiver for det amerikanske forskningslaboratorium og energiministeriet i videnskab og teknologipolitiske spørgsmål. Tidlig i hans karriere arbejder han som rådgiver for Atomic Industrial Forum og har været involveret i udvinding af uran i Canadas eneste uranraffineri. Velkommen indenfor. Good morning, Mark Mills. Thank you for joining me this day. Thank you for accepting this invitation.
It's a delight to join you. And as you know, I was in your backyard just last month in August, floating around the Baltic Sea, visiting lovely Sweden.
Yes, very nice weather.
It was great.
I reached out to you because you are quite an expertise in energy. And I want to talk a little bit about that later, but can you please tell the audience who you are and your background?
Well, what I usually tell people, especially in the modern era, is to use the magic Google machine and type my name, and they'll learn much more than they ever wanted to learn about me. But I started life, I'm Canadian, I immigrated to the United States many decades ago, but I was educated in physics at Queen's University in Canada. And my early career was in semiconductors, fiber optics, missile guidance, lasers. And one time I did real work. I have patents and invented things, built things. And then I migrated into the nuclear industry in Canada. I worked for a company that was the only refiner of uranium, still is in Canada, one of the few refiners in the world, and a mining company. And from there, I ended up in the United States and the Commercial Nuclear Industries Trade Association. And turned out a few months after I arrived in America, the accident at 3 Mile Island happened. So as a young man, I was at that accident for the week and then spent many years defending the virtues of nuclear energy. In a way, I accidentally got into the energy business because I'm fundamentally a technologist and a physicist by training, but everything's about energy. And I'm fundamentally curious about how things work. And you can't know how anything works, whether it's a computer, a car, or a jet aircraft or a spaceship, without understanding the energetics, including how you make food, how you make metals and materials. The energetics of these systems always comes up as something that matters foundationally. So that's sort of what drove me into the energy field over the years. And then I worked in the Reagan White House Science Office. It's called the Science Advisor's Office for those in Europe who don't know that function. It's what's called an executive branch function. Again, I was very young, but it was a great education on how policy works. You know, how governments everywhere have, I learned the same features, even though I came out of the parliamentary system in Canada. What you discovered was that the facts do matter. You know, it's important to have facts, but what matters in politics is spin, self-interest, money, the kleptocracy of people, companies that are looking out for their self-interest. So it was a great education to the intersection of science, technology, and politics. And then later, I got involved in the investment world, advising a hedge fund on technology and energy. And then I was a co-founder of an investment fund, a small one that invested in millimeter wave radars and next generation semiconductors and software. Great education to the third world that matters, which is the money world. So I've spent a lot of my career in all three, and now I am again launched a investment fund, co-founded I'm a non-managing partner, so I have a bias by virtue of the fact that that expression, you have to put your money where your mouth is. So I guess you could say about that. And we're investing in this fund called Montrose Lane in software that is useful to help energy businesses of all kinds. But the biggest energy business in the world is the hydrocarbon energy business, oil, gas, and coal. And it's the one that's the least digitalized. And so the opportunity to bring efficiencies there is something that we invest in. And of course, I'm in the Manhattan Institute, I should say, in virtue of the fact that I'm a senior fellow there, which Europe has some think tanks as well. So it's a right of center think tank that focuses on policies of all kinds, policing, safety, urban issues, social issues, education, but also energy and technology. So I'm affiliated as well with the Northwestern University Engineering School, where I'm a faculty fellow, and occasionally give a lecture on technology and energy, robotics, and finally, I have to say, for your audience, they should know that I wrote another book, a new book called The Cloud Revolution, which is about technology in the coming 2020s. And there are many chapters on energy, but it's not an energy book per se. It's a book about artificial intelligence, cloud computing, material science, and the convergence of these revolutions and what it means for everything from transportation to healthcare. So that was an overlong introduction, but since you told me to tell people, they now know more than they ever wanted to know about my background. So
Yeah, I can put a link to the book in the description for people who are interested. Um, Energy is kind of fundamental to the modern world.
yes,
And for about 100 years ago, we discovered fossil fuels as an energy source. What kind of impact do you see this discovery for the modern civilization?
I think at a broad level of abstraction, you're absolutely right. Energy is not just fundamental. Nothing exists without energy. So everything is society. Everything that exists is the result of the interaction of energy and matter. Everything that we build requires reforming matter with using energy to make something, whether it's food or steel. It always requires energy. Nothing exists without energy. It's the physics of energy actually matters fundamentally. The third variable that goes into what makes civilization possible is information. What we understand about matter and energy allows us to manipulate nature, to do very clever things like make semiconductors or fertilizer. Artificial fertilizers or artificial intelligence are both the result of the intersection of our understanding, knowledge, and the manipulation of energy and matter. I mean, fundamentally, the only difference between us and cavemen, cave women, is that all the same atoms exist now as existed then. All the same energy forces exist now as existed then. Why are we wealthier, more prosperous, and healthier? It's information about those two things. So the goal of humanity, civilization, has been to reduce the costs and impacts of energy. And by that, I mean, if we look at history, 80% or more of an economy for all of history has been consumed by acquiring energy, food and fuel. The advent of the hydrocarbon age, fossil fuels, resulted in that ratio dropping to 15 to 20%. This is the biggest single and most important advance in all of human history, to push the costs of food and fuel into the background so that you free up money for health, environment, entertainment, and education, for more comforts and conveniences. This is the biggest transformation that's ever occurred in history, and it's entirely anchored in hydrocarbons. But for hydrocarbons, the world would still be in poverty, abject poverty, and people would not be traveling, enjoying the comforts, conveniences, medical care that they get, education, and entertainment. But for the fact that discovering machines that can employ hydrocarbons and achieve the kind of economic leverage that's unprecedented in history. So that's a long way of saying the world wouldn't be what it is today if it weren't for hydrocarbons. In fact, just as a starting point, 84% of the world's energy still comes from hydrocarbons. And 20 years ago, it was 86%. So the 2 percentage point decline in 20 years of, a lot of money spent on alternatives is not much of a decline in percentage terms, and it's no decline in absolute terms. In the last 20 years, the quantity of hydrocarbons the world has needed to use and produced has increased by an amount equal to adding the demand of the United States times 2 in just 20 years.
And I guess hydrocarbon, the use of hydrocarbon makes it easier to survive in cold areas like Scandinavia and Canada. It makes us, because we are tropical, humans are a tropical species. We don't thrive very well in a cold environment unless we have some energy like to protect ourselves from cold and the weather and make life possible all over the world, no matter climate or weather events.
Well, energy obviously keeps us warm or cool. The discovery of our ability to cool ourselves. Energy allows us to move water to where we need it, and discover water in different places. Energy allows us to desalinate the ocean in the Middle East, which is a primary source of drinking water in the Middle East and for irrigation. Energy is also what makes possible to build things that we need. You can't build concrete without a lot of energy, a lot of coal, a lot of natural gas. You can't mine things without energy because you have big machines that take energy to build, energy to operate. I mean, in a sense, what energy does, energy machines, is replace the obvious, replaces human labor and amplifies it. So it's not just replacing it, it's amplifying it. It's making the hour of labor become 10 times or 100 times or 1,000 times more economically productive and fundamentally safer. I mean, human labor and animal muscle power are magical things in nature, but they don't have the leverage of machines.
Do you, as an energy expert, do you see the demonization of the fossil fuels, hydrocarbon, as fair?
Well, the demonization of hydrocarbons is it's not that it's not fair in that sense. It's a little silly. It's not. It doesn't make sense. The world wouldn't exist without hydrocarbons. We couldn't. There's nothing that we have that we take for granted every day that would exist or operate without hydrocarbons. Europe's discovering that right now. The incredibly challenging political and economic chaos rolling through Europe is a consequence of the shortfall in hydrocarbons, self-evidently from Russia. But to put it in perspective, the incredibly damaging 1,000% plus increase in energy prices in Europe is coming from a roughly 5% shortfall in energy supply to Europe. The overall energy supply has been degraded by 5% entirely in the hydrocarbon domain, and this is causing chaos. Everything from food production because of fertilizer plants shutting down to car production because aluminum smelters shutting down. So it's so the demonizing hydrocarbons and the idea of combustion, is sort of kind of silly. The point of combustion, burning hydrocarbons, using oxygen to combust them, is to release energy. It's not so the resulting carbon dioxide is a product that they're trying to create, in a sense. The exothermic reaction in physics, the release of heat, which is carbon and oxygen together, is what we're trying to achieve. And we use that heat to make engines operate. And we use that heat to convert chemicals into products that are useful to us, not least food. So it's, 99% of the world's transportation, actually 90, to do it exactly right, 97% of the world's transportation, moving goods, people, food, fuel, is done by burning oil. So despite all the hype about electric cars, electric transportation, and ethanol and biofuels, and all billions, hundreds of billions of dollars spent, here we are today, 97% of all the world's goods and people move by burning oil somewhere.
And eh, talking about my country, Denmark, and Scandinavia and North Europe in general, we have declined their own investment in their own fossil fuels. We have a lot of gas in our underground,
Yep.
but they refuse to use it because of that policy that we will not burn hydrocarbons. We burn wind and solar instead. And now they pay the price because many of the backup power sources have been shut down, like coal and nuclear energy power plants. So now, right now, they kind of like preparing people that there might be some blackouts during the winter, depending of course how hard cold it's going to be, and it is kind of a rare situation because we are so used to just having energy all the time. So this is kind of new situation for whole Europe, I think.
Well, it was a predictable situation. I was not alone predicting this is where we would end up, and we're ending up here not just because of what Putin has done in constraining supplies. It happened, as you know, last fall. The European energy prices skyrocketed, and in Sweden, one of the biggest oil-fired backup power plants came online to keep the lights from going out. Oil-fired, massive. It's the size of a nuclear power plant. It burns oil in Sweden. It's there for backup, not for regular use. Fortunately, it was there. Fortunately, it kept oil stored. But the reason that we had these 1,000% increases in electricity prices last fall was a giant lull in the North Sea wind for about a week, as you may recall in the news. There was no wind in the North Sea, none at all. So all the wind turbines stopped operating for a full week, which caused a massive cascade of high-cost energy and the risk of blackout across Europe. But the more you depend on episodic power, the higher the probability that that will happen. And what is now evolved is that the share of electricity produced in Europe from wind and solar is high enough that these risks become significant. So over a time period of decades, we know for a fact in meteorological data that there are always periods of days to a week or longer with no sun. You know this in the northern latitudes. If you have northern latitudes and lots of clouds, you can have no sun for a month, and you can have no wind for a week. And so if you get your electric supply system using lots of wind and sun without much backup, you get exactly what's going on. So what Russia's cutting off of energy to Europe is doing is simulating the future happening more frequently. But here's the irony, Ricky. The virtue signaling to not burn oil and coal, gas in the Scandinavian countries is it doesn't mean that the oil, gas, and coal aren't being consumed. You've just exported the combustion because the solar panels you're buying, 80% of the modules are fabricated globally in China. Their electric grid, which electricity is used to make polysilicon, is 2/3 coal-fired. The aluminum that you purchase from China is made with coal-fired electricity. And the materials that are put into your wind turbines, neodymium, are produced with oil-burning trucks and oil and gas combustion in China, where the rare earths are mined. The same is true in Africa. So what Europe and the United States are doing is exporting the combustion, exporting the jobs associated with it, by the way, which, in rich countries, people don't care about exporting mining jobs and refining jobs. They don't care. They're happy enough. And frankly, they can afford to it because they're rich, right? But it doesn't mean that the combustion isn't happening. It's just happening somewhere else. The only country that's done an honest accounting of this is France. So last year, before this chaos broke out with Russia, the French government ordered an analysis of their carbon footprint based on counting imports of manufactured goods. So France has claimed that they're meeting, the Paris Accord with declining CO2 emissions. But when they account for their actual emissions that they're responsible for from purchased goods, what the French government honestly pointed out is that their CO2 emissions have actually risen. So the French people are emitting more CO2. It's just elsewhere. This is true in Denmark. This is true in Norway. This is true everywhere because you can't escape the fundamental physics. If you want to make the metals, materials, and chemicals manufacture the things, you'll consume energy. And as I said earlier, we know that 84% of the world's energy is in the form of hydrocarbons. And when you look at countries like China and the rest of Asia and Africa, it's not 84%. It's more like 90%.
And and in Germany, they have spent a fortune on solar wind panels. When you go across northern Germany, you have wind farms and solar panels all over. But despite that, the demand for coal has risen this decades. So it's kind of like ironic that they spend so much money, but still are so dependent on coal. Uh, so this policy about this eager policy, eager to try to base a national power supply on solar wind. Why is it that they are so eager to do that? Because they can see the logic in this, why are they still pushing this agenda forward?
Yeah, this is there's two parts to that question, right? What the why and the what. I mean, I can answer what they're doing and what the consequences are, which we're seeing now, and they'll get worse. Why they're doing it gets out of the physics and engineering and into psychology and politics, as opposed to, I'm sure getting into people's head. Why do they say what they say? Why do they do what they do? I mean, I can be facetious, and simplistic and say it's because they're interested in getting reelected, and it's the popular zeitgeist that what people believe, and they say a lot of politicians say what people want to hear and believe, and there's a big narrative, as you know, that we are in this massive energy transition, and they want to be part of this exciting new future, and they think that's what the future's about. That's exciting. And listen, I'm the same camp. My book, The Cloud Revolution, is an optimistic book. I think the future is very exciting. I think there are a lot of exciting things happening in energy domains, just not the ones that we're spending too much money on. And I think there is a realization now, it's a harsh realization that they can't do what they said. And I think in some cases, I think they weren't being dishonest. I think they really believed the stories they were told. They really believed you could run a grid with lots of wind and solar. Look, I'm from Canada, same latitudes as Germany and Denmark and Sweden. You know what the percentage of the time you get sunlight in half the year. So these solar arrays you're spending money on, their actual duty cycle, the percentage of time that they produce electricity, if you put them in in Italy or Spain or sell them in the United States, they'll produce energy 30% of the time on average over the year. In northern latitudes, it's about 6 to 8% over the year. So you spend, for every dollar you spend in capital, you're getting 10 cents worth of energy production, which is pretty expensive and pretty pathetic. And to your point, you need to have coal plants, oil or gas plants available to fill the gap. So now the fiction that they're selling is, we can build batteries, a lot of batteries. So why would we believe that if we just do some simple arithmetic? And I did this for Europe, by the way. So what Europe is doing right now and has successfully done is refilled its natural gas storage system to ride through a winter that's not too harsh. If it's a harsh winter, Europe's got a problem. If it's not too harsh, you probably get through it with the extra gas put into storage. So what European governments have done, Germany in particular, is rush to build floating LNG gas import terminals that divert gas away from industrial boilers, burn oil instead, or shut the factories down, which is already happening across Europe, and store gas for the winter. But here's a calibration point. We've done it successfully over the last several months, stored enough gas, essentially stored about 4 to 5% of Europe's total energy needs. Put in different terms, it gets you about close to a month's worth of supply. If everything gets cut off, you have a problem, which is good. If you want to store that much energy in batteries, just to give you a calibration point, it's about $40 trillion worth of batteries. $40 trillion. If you took all the world's battery factories and ran them nonstop for 400 years, all the battery factories that exist today, you could build enough batteries to store the amount of energy that Europe now has in storage to ride out a few weeks of shortfall. So the idea that you can run the European economy reliably with batteries doesn't mean they won't have a role. They have a big role. But to make them the anchor, which is the vision of wind and solar, is so profoundly naive. It's dangerous. It's actually a delusion.
Yeah. But the political world also like claiming that they promote solar wind energy because it's sustainable and oil is black energy.
Right.
But it seems like when you look at like electric car batteries and windmills, they use up a lot of like raw materials, like you need like even more than just getting oil from the ground. Is it sustainable in any means?
Well, I think the way we all define sustainable, which most of us do, is the broad umbrella, not just about carbon dioxide, but about how much of the Earth's land we use and footprint, and how much material we use, how much we have to move, how much water we use, all these things, how much chemicals we have to use. So the short answer is the idea that wind and solar and batteries are, quote, sustainable is a fiction. It's a fiction on two counts. First, all machines wear out. When you build a machine, it wears out. It has to be replaced. So there's no such thing as renewable energy. There's no infinite supply that you build a machine and it keeps running forever. So wind and solar machines wear out, batteries wear out, you have to replace them. So what you'd want to know is how much stuff do I dig out of the earth to build the machines in the first place? So as a calibration point, a single electric car, whether it's a Tesla or a Volkswagen or a Volvo, it doesn't matter. The battery weighs about 1,000 pounds for an electric vehicle, replacing about 80 pounds of gasoline or petrol, 1,000 pounds. It takes about 500,000 pounds of mining of ores and rocks dug up, processed, and refined to produce one battery weighs 1,000 pounds. Or put in the IEA terms, as you know, the International Energy Agency has done a pretty comprehensive analysis of the electric vehicle fuel cycle in wind and solar. Roughly a 1,000 to 4,000% increase in mining and minerals are required per unit of energy produced when you go wind, solar, batteries versus hydrocarbons. This is an unprecedented increase in mining, the likes of which the world has never seen. The mining sector is rocked by increases in demand of 10 or 20%. We're talking 1,000% increase in demand for not exotic things like cobalt or lithium, right? But basic things like copper. Copper demand will go up 300%, aluminum demand up 400%, nickel demand up 1,000%. Basic metals that we've been mining for centuries will have demand increases that are unprecedented in history. Where's that mining going to happen? Not in Europe. I mean, the European, EU has proposed to support European mines. There's a huge lithium project imagined in northern Portugal. It's been fiercely opposed by the environmental movement. There are mining projects all over Europe. Europe was the biggest source of metals in the world until the late 19th century. The minerals are still there. You can't mine in Europe. You can't expand mining in North America. So where's the mining going to go? In very fragile ecosystems and fragile political systems in Africa and South America. If you're an environmentalist, you should care about this. And some environmentalists do care about it, and some of them object. So what they're doing is they're helping those communities organize to oppose that. Okay, I can't. How can you object to that? I get their objections. They make some sense. Well, then you still ask the question: where does the copper come from? An electric car uses 300% more copper than a conventional car. When you start making millions of cars that each use 300% more copper, it becomes meaningful. It gets measured into millions of tons of copper a year of excess demand, for which the world is not, and this is easy to document, it's unequivocally the case that the world's mining community is not planning to or expanding mining sufficient to meet the aspirations of the so-called energy transition.
As far as I know it, like mining of lithium and that kind of exotic materials is much more damaging to the environment locally than, for instance, mining of coal because I read that there's quite a high restriction about mining coal. When you close down the mine, there's
Right.
you have to test the water, and then you kind of leave it alone and let nature do its work, and then just kind of monitor it, that everything goes by. But so it seems like you kind of be aware of like conservation like, of the environment, but in that kind of like lithium mines and cobalt, it seems like they not really care that much. And as you say, it's a fragile country, fragile economy. They're not really maybe that concerned about what they put into the ground to get the stuff up.
Well, yeah, you make a very good point, and this again, this comes to where, where we started out. I was telling you my interest in this whole domain comes from unbundling how things work. How do we make a car? How do you make a battery? How do you get the copper? How do you refine it? How do you mine it? And the more you look into these things, the more you discover some basic facts that are unavoidable. Your point about coal is exactly right, and it's anchored in sort of a geology or geophysics point. So when you dig up coal, uh, essentially you have a little overburden, some dirt in the way, or you have an underground coal mine. But then you follow the coal seam; it's all coal. It's 100% coal. You dig up a ton of coal, you get a ton of coal. If you want to get copper, you have. If you want to get a ton of copper, you have to dig up 1,000 tons of the ore, the rock that contain the copper, because well, it's a little less than that, but it's that range. So the ore grades can range from under 1%, so you have 100 tons, to 0.1%. So you, by definition, are disturbing more of the earth, because you have to get the product you want. You want a ton of coal, you dig up about a ton plus 10% of overburden. You want to get a ton of copper, you dig up 100 tons of rock and another 200 tons of overburden. So you're disturbing much more of the earth to get to the minerals. And then the coal you dug up is useful as dug up. You can burn it as is. You dig up a ton of copper ore, you can't burn it. You can't make a car out of it. You have to crush it with big giant machines, use chemicals to dissolve the rock to release the copper, and use chemicals to refine the copper and energy to get that final copper. Oil and gas are the same. You don't disturb a massive area of the earth. You drill a hole in the earth, a foot in diameter, as you know, and go down deep and release the oil and gas to the surface. So your footprint is 100 times lower with oil and gas, and even with coal, but especially with oil and gas, compared to the so-called sustainable route of green energy. So these are totally unavoidable facts that are invisible to most people. So when you asked earlier, what are the politicians thinking? Well, I think they just don't ask the question. I mean, I just mean they don't ask the question of where's the copper coming from? What's the footprint of the copper in environmental terms? And those questions are now starting to be asked, including, to their credit, by a lot of the European political policymaking agencies.
Mm. And when you look at a global scale, it seems like the world is kind of divided into like the Western U.S., Europe, who's eager this policy about solar and renewable energy, whereas Asia and South America seems like they're not just going their own way, especially Asia. They're just pushing forward because they have a huge population who like they raised out of poverty, and their modern lifestyle takes energy. So the demand for energy it goes up, and the only way they can match that demand is by building more power plants. So it seems like they not really share the same view about renewable as in the Western world.
Well, we could be cynical. They're happy that you and we in the Western world are letting them enjoy the economic benefit of them supplying the minerals and fuels we need here. They're happy to take those jobs. I think China is very happy to do this. They have a dominant position in the energy minerals refining area. They enjoy, by the way, a global market position that is twice that of OPEC and oil. That is China's ability to supply the world with refined energy minerals, copper, lithium, and cobalt. Their market share is double OPEC's market share in oil. So they're perfectly happy for us to make these decisions. But your point is exactly right in this sense that I think the biggest difference between the Asian policymakers and the Western policymakers is not that they don't share the idea that alternative energy sources are important and have a role. They clearly share that idea. They spend a lot of money on it as well. But what they don't share the idea is that you can do without hydrocarbons. So this is sort of my, if I have a campaign idea, it's not a complicated one. It's not that I'm anti-electric car. I love electric cars. And I've been to wind farms in China that stretch the horizon. I think they're amazing engineering feats. And I was in, as you and I talked about earlier, I was in a cruise in the Baltic recently, going by a lot of wind farms in the Baltic Sea. They're amazing manufacturing and engineering accomplishments, valuable and useful. Solar power has an incredible role in the future, especially in southern latitudes. But there's no future that's possible without both. So the idea that one is replacing the other is a dangerous fiction. What's happened over history is that we've achieved economic growth by adding energy supplies, not getting rid of old ones. In fact, this is an ironic fact that most people don't know. Here we are in the 21st century. As of right now, burning wood globally, maybe the oldest energy form, provides almost 3 times more energy to the world than all the solar panels combined. Burning wood globally. Now, who's burning wood? Well, actually, they're going to be burning wood this winter in Poland and Germany to keep warm. But most of the wood burning, of course, is in emerging markets because wood's available, it works, and it's cheap. And it's not ideal for them, but we still use a lot of it. And I think we'll still use a lot of it 50 years from now. The difference will be solar will overtake it. But it's not going to fully eliminate it any more than it's going to fully eliminate coal. Coal will be a smaller percentage of the world's energy in the future. That's already happened, and it's going to keep happening. That's not a bad thing. That's actually a good thing because that means other energy forms are expanding. We need a lot more electric cars, by the way, not because we're going to replace oil use in transportation. It's because I don't think we really want a world, and we can't easily achieve a world that produces a lot more oil than we're producing now. We're a 100 million barrel per day world of oil production. This is an amazing number, by the way. I mean, 100 million barrels per day of oil. If you put that amount of oil into barrels, they're not actually in barrels, as you know, but if you put them in barrels, then the line of barrels would stretch 2,000 miles. You made a row with them. So that would be from Copenhagen to Sicily or something. You'd have a line of barrels 2,000 miles long. That stack of barrels would grow by the height of the Eiffel Tower every 5 days. If they were barrels, that's how much oil the world produces. We'll produce more because we'll need it, but you can't fuel all the future growth just from oil because the demand will be too great. And think about this. In Europe and in the United States, for every 1,000 citizens, there's about 800 cars. Or put differently, there's more cars in Europe and the United States than there are licensed drivers in both countries. But in the rest of the world, where about 7 billion people live, there's about 20 people per car. Right? There's one car for every 20 people. They want cars. I'll bet you half those cars will be oil-fired. If half of them were electric-powered in the future, okay, great. But that means there's a net increase in oil demand for cars, not a decrease. That's what that means.
Yeah. So there's no doubt that the development we see in India and China and many South American countries, that the demand for energy, our modern lifestyle, it takes energy, and demand will go up. How do you see that? Can we secure that? What kind of technologies do you see can be the, if not fossil fuels? Is there anything out there that sounds like promising new technologies or new ideas that you see is upcoming to maybe be a supplement or take over in the future?
Well, sure, but in the physics of energy, you sort of have to start with the two different domains. One is what fundamental forms of energy exist that we can tap into. And when it comes to that, well, there may be new physics one day. We'll discover what dark matter and dark energy are one day or something. Who knows, right? There'll be new physics. But right now, you have to deal with the physics we know. And there's only 3 things you can do. You can burn something, whether it's coal or biofuel. You can convert motion into useful power. whether it's wind moving or water moving, doesn't really matter, right? Or you have atomic phenomenology, which is photovoltaic effect, solar, and nuclear fission. If you look at the pantheon of things that are available, the only thing that's remarkably better than everything else we're using is nuclear energy. It reduces the footprint on the planet by 100 to 1,000 fold compared to 100-fold less than combustion and 1,000-fold less than solar in terms of our footprint on the planet. So the nuclear option is now being rediscovered and re-examined. People talk about hydrogen, which is, we'll use more hydrogen, but it's kind of silly. It's a very, very expensive intermediate form of energy. It's not much different than electricity in the sense that we don't capture electricity, we make electricity. Electricity is an intermediate carrier, if you like. It's not primary energy. Hydrogen is an intermediate carrier. You have to use energy to make it. In materials, it's very expensive. People, but the future is going to involve two things: more efficient ways to use energy that we already know how to do. For example, more efficient internal combustion engines, more efficient aircraft, more efficient processes in industries. That'll happen, especially with, and I write about this in my book again, about artificial intelligence and intelligent automation. We're discovering always new ways to improve efficiency with existing systems. That'll keep happening. I think it accelerates, which is a very good thing. On the other side, we'll develop better materials to improve the efficiency of combustion. If you can cut in half how much fuel you have to burn to make a unit of electricity or drive a mile or fly a mile, that's consequential. And we'll find better solar photovoltaic cells, and we'll make better batteries, and we'll make, these things will all happen. But there's no magic bullet. This is the key thing. There's no thing you can, this is the solution to the world's problems. There is no solution if the problem is not using hydrocarbons. If that's what the problem is being defined as, there is no solution for that. If the problem is, can I reduce my footprint? The answer is yes, you can. It's called technology of efficiency, and the technology of we'll call it production efficiency. That is reducing not just the inputs per unit of energy output, but also improving the longevity of the machines themselves, because then you don't have to use as many materials to replace them. They last longer. You could improve the efficacy with which we operate our systems, which is the Uberization, if you like, of the world. The danger of Uberization in just-in-time delivery, which is very energy efficient, is when there's a disruption from nature or a war, things fall apart. So you have to sort of balance that with resilience, which costs money and costs energy. So it's a long way of saying, do I see anything exciting? Yeah, a lot of exciting things, but not the way that people define them as getting rid of oil, gas, and coal. That's not happening.
No, I see a lot of small projects, but usually it's like experimental, and when you blow it up to become like a support a national power of demand, then it either too expensive or not developed enough to be stable. So maybe in 10 or 20 years from now, do we know the argument for replacing fossil fuels is also that there's a certain number and a certain amount of fossil fuels in the Earth's crust that we can use. Sooner or later, we're going to run out of it. Do we know like how much there is left there? Is there some kind of estimation how long we have left of fossil fuel like coal and oil and?
Yeah, well, that's a good question. Let me first just amplify something you said that's really important, Rick, about the timelines from innovation to practicality, scaling. The scaling challenge is really a very important and poorly understood feature. It takes a long time to take a new idea, commercialize it, and then scale it up at society levels. And maybe the best example of that was the invention of lithium chemistry for batteries. That was a big deal. It's 400% better than what came before for the last 2 centuries. And but as you probably know, lithium chemistry was discovered as a viable battery in the mid-1970s by Exxon, by Whittingham at the research labs in New Jersey. It didn't get commercialized by Sony until the early 1990s, so not quite 20 years. And then the first practical, expensive electric car didn't come around for almost another 20 years, the Tesla. And here we are almost on the 20th anniversary of the Tesla coming up in 50th anniversary the introduction of the Tesla S, and we're at what, about 1% of world's cars being electric. So you just think about 50 years roughly since the discovery of the phenomenology to begin to have market penetration at scale. That's very typical of all technologies and at society scales. Those kinds of timelines, decades, not a few years. It's true, by the way, of the internet. We trace its roots. It's exactly the same kind of timeline to have impact. But the question you ask about how long will hydrocarbons last? How much oil, gas, and coal is in the world? So we know based on the technology we have today, which is an important caveat. Using what we have today, knowing what we know today, that we have hundreds of years of supplies of hydrocarbons, not tens of years, hundreds of years. The question about what's the ultimate resource base, it's an interesting academic question, but it's irrelevant. We have hundreds of years of supply, and as we get more efficient at using existing supplies, both economically and environmentally, by the way, it matters about our footprint efficiency. Then those supplies will last longer. We'll extend them. And once you talk more than 100 years of reliable economic supplies, we're into time frames that are completely irrelevant to worry about for us in the present, because you have to believe, because of what history tells us, that we'll have a lot of impossible to anticipate inventions in innovation and science over the next century that will moot the question, how long will it last? But to answer the geophysics question that you're sort of teasing about, how much of the stuff exists on Earth, because it's, the trope, it's finite, it's melted down dinosaurs, and we're going to run out of this stuff. Okay, all things, you run out of what you found, right? I mean, resources are not uniformly distributed, so that's true. It depends the depth you go for oil and gas, and how far you can go down, and where you're allowed to explore. I mean, in Europe and North America, you're not allowed to explore anymore. It's illegal. You don't even know what's there. So saying what the reserves are is meaningless, because you're not allowed to go looking for it. And we know if you go looking for it, you'll find more. But let me beat to death the notion that we don't have limits to hydrocarbons as a fundamental resource with an interesting observation. Natural gas is supposed to be a fossil fuel, of course, right? If you may recall, when NASA's Cassini probe flew by the moons of Saturn, they discovered that it rains natural gas on those moons. There's oceans of liquid natural gas on Titan. So now, if there's oceans of liquid natural gas on the moons of Saturn, and it rains natural gas there, if you think these are melted down dinosaurs, you'd have to believe they got space travel and flew there to die. Obviously, liquid natural gas is also it's a fossil fuel, but it's also a naturally occurring fuel.
Mm. Yeah. I once heard someone said that the phrase that usually we not stop using wood because we run out of wood. It's because we find something better. We develop. We find some new technology that's more efficient. But nuclear power, in my point of view, seems like the obvious substitute for fossil fuels, because we also use fossil fuels for stuff other than energy.
Right, feedstocks to manufacture pharmaceuticals, biochemicals. Yeah,
exactly. So nuclear energy seems like the most promising energy source for the future to save the fossil fuels for that. How far are the development in the nuclear energy industry at the moment now?
To your point about the role of hydrocarbons, gas and oil in particular, as feedstock to make things, the IEA's latest forecast for the future demand for oil and gas, the largest single source of new demand is a feedstock, not as a fuel to burn, in terms of the rate of increase, because the world needs the stuff you can make, including, by the way, fiberglass blades on wind turbines. For those who don't like plastics, so remember the to stop using plastic straws ran over the world. And when I was in your country recently, it's true in our country now. It's hard to get a plastic straw. They give you a paper straw. But here's a chemical fact and a physical fact. One small wind farm, 100 megawatt wind farm, which is a very small wind farm, tiny. The plastic blades on that wind farm are not recyclable. And there's more plastic in that small wind farm than all the world's plastic straws combined. So for the plastic warriors, they're focused on the wrong thing. But to, the answer to your question is that the promise of nuclear energy is far more exciting now than it has been at any time in the last 50 years. So our ability to build the current class of nuclear power plants, the kind that exist in Sweden today, in the United States, these large 1,000 megawatt so-called pressurized light water reactors. These are extremely reliable, long-lived, very safe power plants. But I sort of think of those in terms of jumbo jet terms. I mean, if you think about these giant power plants, is equivalent to an Airbus A380 or a Boeing, a 777. They have incredible utility, but they don't solve all transportation functions, right? We don't all fly in A380s. We fly in smaller planes and use cars and use ships and airplanes. I'm sorry, in trucks, trains. So the nuclear world essentially right now is comprised only of A380s and 777s. What we need are all the other forms of machinery at different sizes and utility function. There's probably 100 different designs right now at various stages that fall across that spectrum from what I would call a sort of a car, literally a bus-sized nuclear power plant. I don't mean a bus powered by a nuclear power plant, but a nuclear power plant the size of a bus, or a container. So of the 100 designs, they're all technically feasible. So none of these designs are pie in the sky science fiction. The question will be how many of them are commercially viable. We can make at scale, essentially in factories and afford. 20% of them probably. So you'll have 20 new classes of designs, and they'll all emerge in the coming few years to decades, being proved viable. So it's very exciting. I mean, imagine. I think some people like MIT have decided to relabel these smaller nuclear power plants as nuclear batteries. It's kind of a clever way of changing how you think about a nuclear power plant. That if it can be bought and turned on, has an on-off switch, it can't fail. It has no accident mode. It only needs fuel every 20 years, and it has an on-off switch. That's kind of like a nuclear battery. And if it's, let's say, a megawatt or 10 megawatts, that's enough to power a data center or a small town or city or a neighborhood. You bury it, turn it on. That's magical. I mean, it's really important. It's a game changer in many respects, but to tamp down people's enthusiasm about that solving all the problems, keep in mind that about 20% of the world's energy is in electricity form. So even if we double that, which we probably will eventually, because in your country and in America, nearly 35 or 40% of all energy is in electrical form. But you still have the other 60%. That's not in electrical form. It's in a combustion form. To your point, to make concrete, steel, you have to still combust, and we're going to have to do that for a long time.
How far is the technology? But that salt reactor, that the new generation reactors. How far is it? Yeah.
Well, I mean, it'll work fine. We know. Look, there's a whole set. When I say different kind of designs, I mean there's high temperature gas reactors that use helium instead of water, and graphite cores that can't burn. There's the molten salt. There's thorium reactors. There's so-called fast reactors. There are traveling wave reactors. I mean, there's all kinds of new variants on how to capture and deploy the energy inherent fission. Basically, you're releasing Einstein's formula, right? The E equals mc squared that everybody learned in school, but they forget that's what the c squared means. That's the speed of light squared. I mean, the energy density of uranium, in fundamental terms, is more than 1,000,000-fold higher than the energy density in what carbon, common hydrocarbon and fuels and the way we use them. So the techniques to find new ways to take advantage of that across a lot of spectrum. Whether the molten salt reactor is economically practical is the question. Not can you build one? They'll work. The question, how far along are they? They're a long way along. And in fact, one of them that's being built, as you know, in the Wyoming in the United States, I believe. I think it's the Bill Gates funded reactor. Uh, it'll work. I don't think there's any question whether it'll work. We know these things work. Can you build them? The one thing you said earlier that I amplified on, can you build them at scale so that they're reliable and inexpensive, and inexpensive enough, right? Because these things will run a long, long time. I don't know the answer to that. We won't know until we start building some. We figure out whether or not we know how to really build them at scale.
There's a lot of debate now in Denmark. We refuse to build nuclear. The kind of political environment has denied nuclear power since the 80s. Yeah, but now it's kind of like because of this energy crisis, Germany's talking about building more, like rely more on nuclear. So, but there's still a lot of scary stories about nuclear energy, and people still kind of see nuclear energy as nuclear weapons. But so they always, like in the news, always use like Chernobyl and Fukushima and 3 Mile Island as an example why you should not build it. So is that is the nuclear energy safe?
You know, the safety question is, of course, what I spent a lot of my early career on when I was very young. I was at the accident at 3 Mile Island, and that spent a lot of years defending the virtues of nuclear energy. And the issue that comes up most often is safety, and then it's the nuclear proliferation, the weapons relationship question. And those tend to be the two questions that are in people's heads, setting aside people who are either really dishonest, there are some of those out there, or are really ignorant, and they believe things that are just silly. There's a lot of mythology about nuclear energy. Some of that was built up in the 50s, both in terms of the beginnings of the Cold War and worry about a nuclear wars, which we should still worry about, obviously, because there are no more frightening weapons than nuclear weapons. But whether or not there are more nuclear weapons in the world in the future has essentially nothing to do with whether or not we build nuclear power plants. That was initially the linkage. If we build nuclear power plants, we encourage building of nuclear weapons. Well, there obviously is a relationship in terms of the physics, understanding the physics, but these are totally unrelated phenomenologies. In a way, you could say it's like you shouldn't study chemistry to make pharmaceuticals, because chemists can also make chemical weapons. It's true. If you're a chemist, you know how to make pharmaceuticals. Fertilizers, you can learn how to make chemical weapons. But that you can learn how to make chemical weapons without ever doing the other, which is the same. That's sort of the simplistic analogy in what I call the geopolitical piece. The more important one is what I found when I went to the accident up 3 Mile Island. What reporters are asking, what people, everyday citizens were asking, was the one that's in people's heads: will it blow up? Will it be like a nuclear bomb? Because that's what's in their heads. And of course, it's physically impossible. It's not a design feature. A nuclear power plant can't blow up like a nuclear bomb. It just physically can't. And the only reactor that can have the horrific kind of fire, which was a fire, not a nuclear explosion, was the Chernobyl-style reactor, which was a crazy design, which no one's building, nobody else builds. The kinds of reactors that exist in Europe and the United States and around the world cannot physically explode. They can have accidents. But if you have an accident of the class of 3 Mile Island, there's a multi-billion-dollar accident that did not harm a single human being. Nobody, no one was injured, no worker was injured. You'd be hard-pressed to name a single industry, never mind just energy, where you could have a multi-billion-dollar accident and not kill anybody. So is it safe? Yeah. Is it perfect? No. Fukushima, the only public, obviously there were some serious injuries to workers who were exposed to high radiation levels, but from the citizens' perspective, the only deaths that occurred were accidents during the rushed evacuation. They didn't need to evacuate anybody. There was no medical reason to do that. If they had not ordered a panicked evacuation, there would have been no deaths. So, is it safe? Yes. Is it safe enough? Well, this is always a question, whether it's airplanes or hydro dams. You want things to be safe, but nuclear energy has some features that make it, on a relative basis, safer than than most. In fact, in many respects, when you count the whole sort of the whole ecosystem, if you like, one of the safest forms of energy we could imagine.
Mm-hmm. How about the building a power plant in Denmark? One of the arguments for not rely on nuclear is because it takes a long time to build it and up running. But in France, they do it like in 5 years.
Yeah.
So is that your experience in the US also, that it takes around that time from plan to up and running?
Well, this is exactly the problem. If you build an expensive machine that costs billions of dollars, and you delay it for regulatory and political and reasons, then you make it more expensive. So the key to any capital project, doesn't matter whether it's a factory, a mine, a commercial building, is if it costs a lot of money, you delay its construction, it'll cost more. So the solution for nuclear energy is actually a political regulatory solution. You don't have to get rid of safety standards. You just have to be more sensible. Build them more the way the French do and the Chinese. I mean, the Chinese are building more than 100 reactors right now. They're not going to take 10 years to build each reactor. They're going to build each one in 3 to 5 years, which is technically doable. And if you go to the smaller reactors for other purposes, right, not these big power plants, then you can imagine building the small reactors in the same length of time you build a jet airplane engine, right? You build them in months, not years.
Many talk about the nuclear waste, as I know it, like many nuclear power plants can actually recycle the waste. Is that true?
Well, you can reuse. So the nuclear fuel is considered quote waste or unusable when it's got sufficient contamination, what are called fission products from the fissioning process. So you can recycle the fuel and reuse the uranium that's unconsumed. So you only consume a small portion of the uranium. So that recycling can be done. It's quite common in France. It's called reprocessing. Or you can just store it. It's a ceramic-like glass material. The quantity of waste is trivial and easy to monitor. So a lot of the fears about nuclear waste are pretty much, again, the hype and overblown.
And maybe because people have an idea, it's like kind of like a green liquid that glows, like it does, like maybe in a cartoon. Maybe people don't have really an idea how it looked like.
Well, that's why I say it looks like physically like a piece of ceramic. That's what the waste is. So it's like glass-like material that is tiny in volume. So you reduce the amount of waste produced per unit of energy again by something like 1,000-fold compared to every other process. And because it's radioactive, it makes it dangerous. But because it's radioactive, it's easy to monitor, easy to isolate. So it's an irony. Well, this has been interesting, a lot of fun. I really appreciate it, Greg. You're giving me the platform. I hope people listen.
Looking forward, what would you advise the political environment in the Western world to do from now on, in the light of that this new energy crisis and relying on solar wind and refusing like demonization of hydrocarbons? What if we should look in the future? What kind of advice would you give, like the Danish government, how they should proceed from now on?
I tried to give the Swedish government advice in 1980 not to vote to shut down nuclear power plants, but obviously I was too young to be believed. And anyway, so I would put the advice in two broad buckets. Do more of what they're doing right now in Europe, which is an incredible refocus on bringing in natural gas or LNG terminals, the floating LNG terminals, reorienting pipelines to the south, which is, already happened. In other words, there's an expansion and recognition of the need for hydrocarbons going on right now in Europe. But no one is abandoning their goals and vision about solar and wind and batteries. My advice would be to keep doing that, do both. So the path that Europe's on now, forced on Europe by the X-ray of the Russian invasion, is the path that Europe should continue on for the near future, because that's the only future that's viable. We need both. Europe needs to increase its resilience and reliability of supply of hydrocarbons from somewhere. I think Europe should do what new Prime Minister of the United Kingdom is now doing, which is, reopening the possibility of domestic drilling both on land and offshore, North Sea. I think it's unfortunate that the Netherlands is going to continue to shut down the Groningen gas field. I understand why they're doing it, but I think that's a mistake, personally. But you can offset that with more imports. So the near term is do more of what's already going on. You don't have to abandon the goals of more electric vehicles, but you have to increase the resilience of the supply of your fuels for your combustion vehicles. You have to do both. For the longer term, the transition that everybody wants, the key piece of advice is patience. We want to have something happen quickly that can't happen quickly. We can mine enough minerals to achieve these visions, but it takes a lot longer than people think. And we can mine them safely and cleanly. It'll take longer than people would like. You can't do it in a few years. It'll take decades. We can make more nuclear energy. We'll probably crack the code of fusion one day, but it'll all take time. And more time than the policymakers would like. They need to be more honest about the need for patience on the transition, and they need to be more honest on the need for hydrocarbons in the short term. I mean, that would be my advice. And I think most people are adults. The extremists who don't, just say we have to keep abandoning hydrocarbons have been exposed as being extremists now. You can't do that. It's economically destructive. It's morally damaging. And people will be freezing to death literally this winter if it's a cold winter. People will be starving around the world because of the loss of Europeans' fertilizer production. It's not just the loss of Russian fertilizer production. European fertilizer plants are shutting down because of the cost of hydrocarbons. This is profoundly dangerous and immoral. And I think reversing that is important. So if the advice is treat citizens with a little more respect, tell them the truth, in a sense, that you need both and we need patience, might be my principal advice to politicians on both sides of the Atlantic.
I've seen some projects about deep earth crust drilling. Like they want to harvest the heat from the inside of the earth. Is that something you see as a possibility in the future?
Sure. Well, geothermal energy, tapping the heat of the earth has always been possible. Iceland has the easiest task of it because they don't have to drill very far. Look, the simplistic version of the geothermal heat pumps, the surface heat pumps that use the phenomenology of capturing cold and hot differentials, they're very useful, very practical, but they don't change the world. The energy costs and the materials requirements to do deep earth drilling to tap into the Earth's heat are extraordinarily expensive and challenging. People are profoundly naive about how difficult that is. But will we do more of it? Yeah, sure. It'll be in the same bucket of another add-on. And in those parts of the world where the heat isn't that deep, because it just depends on the depth of that you have to go. But as you go deeper, we encounter pressures and temperatures for which we don't have practical materials to operate on a reliable basis. But there'll be more of it. Although I would say this is kind of ironic, those who promote geothermal energy often are the same people who oppose drilling for oil and gas in Groningen.
Yeah, yeah, ironic. But I guess the development it's good that people are trying to get new ideas, because just like space travel, it promotes development and new ideas, and that's good for everyone.
Of course.
And some will survive and some will die out, and but in the long term you have to be a little bit realistic and maybe more patient about what can be done in the real world.
Well, also in the long run, because none of us are smart enough to know exactly what's going to work, having governments decide by fiat, by dictate or diktat, what energy sources are the future is a mistake, because they aren't smart enough to know. So we have to have an economic system that's flexible enough to allow trying lots of things and failing at things. But that doesn't come. The government's response is, well, we'll try it, and we'll use taxpayers' money to do the failing and trying. Okay, a certain amount of that is reasonable. It's always about degrees. But if that's the only path, and they guess wrong, and Europe guessed wrong, we know, by thinking that wind and solar would keep us from keeping Europe from having to use hydrocarbons. I mean, 70% of Europe's energy still comes from hydrocarbons somewhere, just not a lot of it from Europe.
And like you said earlier, that the politicians are not objective on the subject. They have their own interest, and they want to be re-elected, and also many so-called physicists and scientists also become like politicians. So
Sure,
it's kind of it's kind of difficult to maybe us for the politicians to navigate in this, because it's a complicated subject. To get a full depth of what it actually means. So
you're right, and it's actually a fair point to make that it is complicated. But I do think that there are some fundamentals that are not complex. But it's not. If one stays the basic principles of what we're trying to accomplish, which is the society needs cheap, reliable energy, and if we keep asking, politicians and citizens keep asking the question, is it cheap and reliable now? When will it be cheap and reliable? What does it take to make it cheap and reliable? Looking for answers in English and not complex computer models, if you like. Then we might get to a decent solution. But it is hard, and I don't belittle the challenge that policymakers have. Let's just assume that there are lots of policymakers I've met, and you have, I'm sure, politicians who are well-meaning and they're honest. It doesn't mean they all are, but they exist. But they don't have necessarily the capacity to get to the right answer. And to your other point, a lot of people have their own interests, whether they're scientists, engineers, or industrialists. Obviously, they have their own political interests and their own business interests. And so that's the nature. Fortunately, most of the countries you and I are talking about are democracies. That's the hard part of the democracy, is these arguments. So we have to have the arguments and the conversations like you and I are having, and rather than doctrinaire positions that we must get rid of hydrocarbons. Okay, what does that entail? I mean, what is it? Who's going to pay for that? Now, what emotional, personal, financial, environmental cost will we have?
And when I hear, especially many of our politicians like promotes this idea that we should all rely on wind and solar, and the developed countries, they should also have wind and solar, but actually, poverty relates much to the lack of access to cheap and reliable energy, and solar and wind is not cheap and reliable. Fossil fuels is cheap and reliable. So if you want to raise people out of poverty, you should give them access to fossil fuels.
Well, in fact, back to my principal thesis, you give them both. So if you have no grid at all, and you have no significant capital, solar can make a lot of difference to a lot of poor villages, as you know. But then as they expand and their economy grows, they have to meet the energy demands of becoming a big economy. They need grids and they need hydrocarbons. So they need both. And, the magic of how much cheaper solar has become is that it actually functions as like a priming the pump, so to speak, of economic development in many of these poor parts of the world. So I have a colleague who goes around the world to poor regions to help them put solar in and batteries just to get some electricity, so they can get cell connections, so they can get some lighting. And then as they get more wealth, what they want is a car, they want a refrigerator, and now you're getting into grid scale power, which requires hydrocarbons. So that this bifurcation is, again, I'm beating it to death. It's one or the other. It's not. And the mix that makes sense depends profoundly on the stage of the economy and geographically where it is on the planet.
Where can people find your work if they're interested in looking at some of your stuff?
Sure. Well, they can go to the Manhattan Institute website, which is easy to find, and my work's there. They can also go to my website. I have a personal website called Tech Pundit. So it's tech-pundit.com, where I post videos of most of what I've written in my reports and articles and things like that. My books there, that kind
of thing. Okay, excellent. I will put links in the description below so people can find you. Mark Mills, I will thank you a lot for doing this. Spending time. It's been a pleasure.
Well, thank you for having me, and good luck this winter.
You too. Take care.
Take care.